So my talk is going to have a couple of live demos, but one of them I'm just going to go through and reproduce a script I wrote earlier, so hopefully nothing will go wrong. And I'm also going to do a small demo of a package that Roger mentioned this morning, which shows how far we've come in the last 20 years. So I think everyone in this room is very, very lucky to be using R now. There's so many tools available to us. There's so many tutorials online. And I think it's fair to say that R has become much more user-friendly. Some of us can remember the first time you interact with R, you just have this black screen of death. And you just start typing in letters at random and hope that some kind of result comes out. We've come a long way since then. And this is really the context in which this talk is set. I'm not going to talk about the history because Roger covered that in a huge amount of detail and knows it a lot more than myself, but it's very important to understand something of the history so we know where we are and how to move forward and be aware of the direction that things may be going in. But this presentation, the main emphasis or the main motivation for it is this book project and called Geocomputation with R. I know some people have already heard of it, so that's fantastic that people have discovered it online. And basically, we wanted to create a resource that would be useful, and we thought, well, if we just make the entire book open to everyone worldwide, then we are helping to reduce the barriers to entry to geographic data. We are all big advocates of open source software. We're all big advocates of reproducibility. So we said, let's make a completely open source book project, which is what this presentation's about. I'm going to provide an overview of geocomputation with R, but it would be a bit boring if I just listed off the table of contents of a book. So I am going to provide a little bit of a taster of what doing geocomputation in R feels like, and hopefully this is a good kind of taster and something that prepares people for the sessions later on. We've got a R for Spatial crash course tonight for people who maybe don't feel like they're experts already, and then we've got a whole load of amazing presentations coming up and workshops over the next week where a huge amount of information that's at the cutting edge of R spatial, I think, will be disseminated, which is fantastic. And I can say myself that these workshops are really worth going to. I attended GeoStat for the first time in 2015 in Lancaster, and it felt strange going to a summer school in Lancaster where it always rains, but I had a great time anyway. And I think the weather meant that I learned a lot more R for spatial than I would have if it was one of these fancy locations that Tom was showing in his slides. So let's move on. In the context, I'm Robin Lovelace. I'm a geographer. I have some applications to transport data, which I think is fairly unusual in this kind of community. And it's interesting to see that although geocomputation got lots of upvotes for a topic that people wanted to learn about, transport data, I think it got 17 votes. So I guess there's not that many transport researchers here. But that's kind of my domain of expertise or domain of application. But I'm a geographer, basically, and I'd say a general-purpose geographer, which is good. And in the context of these slides, I'm 1/3 of a book project. And the other people who are involved in the book are Jakub, who's here, and Yanis, who already got a mention this morning. And unfortunately, he can't be with us today, but he will be with us on Wednesday when we'll be talking about, we'll have a series of workshops that are kind of inspired by this book project. So we're going to be talking about the book a lot, and this is myself. So you can see here that each of us, we teach R, and our emphasis is on communication, but we also do some development. So each of us has got a package, and we all try and be a participator in our open source community. And I think that's really important. It's easy to get involved now, especially with GitHub. You can, even if you're not writing code, you can open issues, you can provide use cases, and there's many, many ways to get involved. And all of us are involved in the community, not just writing this book. You can see we've got a hex sticker already, which is kind of cool, that Jakub and Yanis made. But we've also, we thought that for a front cover of a book kind of looks a bit empty. So in addition to the spatial prediction competition, if you like making maps and you like visualization, you can try and create some kind of visualization. And the winner, and we'll also be publishing this online, will get to go on the front cover of our book. And possibly an even more exciting prize is you get a $150 voucher from CRC Press. And as Edza mentioned this morning, there's a new book about geographic data visualization just been published by Oscar Perpignan. And I would like to think that that book costs less than $150. So you could buy that book if you win this prize. So this is a parallel project for people who like spatial data visualization. And that's something we should say at the beginning of the slides also. So yeah, we're a team, and although we do some development, we see our role primarily as communicating and helping people to bring together this complicated jigsaw of spatial data in R. So that's really the role of the book. You've got raster package, you've got SF package, and then you've got loads of applications. And a lot of people, this is how I learned, go through life learning just by Googling every time I hit an error message. But there are advantages to learning in a more systematic way. So that's the reason for writing this book, and we hope that it'll be useful. You can find the book online. It's really not difficult to find. Just look up Geocomputation with R. Specifically, though, these slides, Tom asked us to make all of the slides available. So if you want to take a look at the slides or you can't see them clearly, you can navigate to geocomp.github.io, and we've got some presentations here. And hopefully, it's not the most up-to-date, but it's mostly up-to-date. You should be able to see these slides online at this Geocomp website. And we've also got the source code, so hopefully these slides are reproducible. If you want to reproduce everything that is in the book, we've got a GitHub meta package. We removed the code for the meta package from the book because we discovered that every time someone wanted to install the book, they were also downloading about 10 megabytes of data associated with the book, which is very inefficient and wastes a lot of electricity. So now we've moved that to a new repo called geocomp package, and that will just install a whole load of geospatial packages, a little bit like the RSpatial task view that Roger mentioned, but with fewer packages in it, basically. So yeah, that's enough about reproducibility. I'll be providing a small reproducible example that has some example data in it, and you can download that from the slides. But let's just talk about the book for a bit. So this is the overview of the book part of the presentation. In a way, it began with this, which is a Polish book written by Jakub here, and he decided that as he was doing his course notes for geostatistic course he was teaching, I guess he just decided to try and put the notes in the form of a book, which was amazing, and I'm sure that has been used by many people, but I have no idea how to read this, but I discovered it online, and so that was one thing that showed you can use this book down package for publishing geospatial data. Another origin of the book is that I have a repo that's, I think, still my most popular repo, even though it's kind of quite old, but I started teaching R for spatial, and I just had really introductory stuff in there, like how to make a map, how to do a spatial subset, how RStudio works, and I just decided to dump it online, and you never know, someone might find it useful. And next thing I know, it's become really popular. People are asking questions. So it just shows if you put your stuff out online, you never know what's going to happen. And Obviously, I've learned a lot since I wrote this, about 4 years ago, probably. And in the back of my mind, I was like, wouldn't it be nice to do an updated version of this Creating Maps with R tutorial, and especially talking about the new developments in R spatial, specifically the SF package, which Edza mentioned in his talk. So that was another motivation. Both of us wanted to create a book. So we joined forces in Poznan. I think I've just stepped on something. So that was the second origin, that I'd created a tutorial. The third one is based on our third author called Yanis, who joined us quite late in the day, and he's got a package called RQGIS, which is one of these bridges between this is a paper that he's got published in the R journal about this bridge between R and QGIS, which is a common desktop GIS software. And he published this. I was really interested in this RQGIS package because I love QGIS and I also love R. So the fact that there's some kind of interface between these two was really interesting. So I decided to write a message on his GitHub page saying, "Oh, will this be available? Do you want to talk about it in this book?" And to my surprise, the author of RQGIS responded with a huge amount of enthusiasm saying, "Oh, I came across your book project. I've always wanted to write a book about R and spatial data. Can I join your team?" And my initial response was, well, Jakob and I have started this project already, and I don't know if we want a third author. It might make things a bit complicated. There's a common saying in English that three's a crowd. But eventually, he said he could add all of these amazing things to the book, like his expertise in GIS specifically and R bridges, and also the link to ecological data, which Jakob and myself don't have much experience. So eventually, he wrote a chapter for us, which this illustrates his first commit to the book, by the way, and we said, yeah, please do jump on board. So in the process of writing the book, we haven't just been spending our time writing the book. We've also been looking ahead and upstream to all the packages that we're writing about. And as Edza mentioned, it's not just the tidyverse guys. Everyone who writes code sometime is going to break someone else's code, probably. So we've had to fix the book countless times because someone makes a change in their package and then it breaks our book. And that's led to us making lots of contributions upstream. Usually it's just like, hey, why is your package broken? Why have you broken our book? But sometimes we try to make more constructive feedback like, oh, if you do this, it will work in a different way. And a great example of this is Jakob has ended up making many contributions to the TMAP package, which is a visualization package. So the point of this slide is just that we've been contributing upstream as we've been writing the book. So we've been learning ourselves, teaching ourselves the packages, and we've been using the development version of various packages so that we're using the cutting-edge functionality and hopefully teaching people stuff that's up to date. And because it's all online, any time that a package changes, we will change the code so that it works in the long term. So a little bit about the title of this book, Why Geocomputation with R? Well, we can break that question into two parts. So number one is, why geocomputation? Well, it does what it says on the tin. It's a simple word. We're doing geo and we're doing computation. So there's no ambiguity in what we're doing. And we wanted to make it quite a general package. So we wanted to teach the basics, but we wanted to teach basic foundations that you can build on. And the other reason is there's emphasis on tools, so building geographic tools. And it's also, there's a loose link to Leeds as well. So the word geocomputation, I believe, was defined in 1996 in Leeds. I'm based in the University of Leeds. And Jakob and I met up in the 2017 Geocomputation conference. So it just seemed like an appropriate title. But as Edza mentioned in his talks, there's many other ways, there's many other synonyms for the same word, roughly. But we like the word geocomputation. Why R? Well, all of the authors of the book speak the R language, you could say. It's good for academic research, so we're all in academia, more or less, and it's fantastic for reproducibility, and this is something that's really important for scientific research. Science depends on falsifiability, and you can only falsify someone's research if you can reproduce it and demonstrate that it's wrong. There's so many academic papers where they tell you that there's a result, and then they rely on trust that they didn't make some mistake in the programming. So it's really important for us, this reproducibility element. And of course, it's a good language for bridges. And what's really important for us, which makes the process of writing this book really fun, there's an amazing community. And I think everyone in here in some way is part of that community. And we've just got so much constructive feedback on writing it. So it's just a fun project to be involved in. So let's just delve a little bit more into geocomputation. I'm not going to get too philosophical about the history, but there are specific reasons why I like this word. So I went back and got a book written in 2000 before I was doing any of this stuff. And there's a quote here by Stan Openshaw, who was a very creative and innovative researcher based at the University of Leeds at the time. And he says it's about using the various different types of geodata and about developing relevant geotools within the overall context of a scientific approach. So a very broad definition there, but he's talking not just about doing things, but also building tools so that other people can do things as well. And I think the fact that he's mentioning scientific in there is important. We've got another definition here. Sorry, no, we don't. We have one way in which our definition is different from the early definition of geocomputation, because when he wrote this book, he's got loads of examples in the year 2000, but as Roger mentioned, it was all written in Fortran, and to reproduce Fortran is really difficult. So he didn't say, oh, just run this code on your computer and you'll be reproduced. You probably had to have a mainframe computer this big to reproduce the stuff that they were doing in the 1990s. So a difference is that it was unrealistic to expect readers to be able to reproduce code examples when the term geocomputation was created, but now it's possible to realistically expect to reproduce at least part of any scientific analysis. Another part of the definition is that when you take a computational approach, you can be more creative. That may seem like a contradiction, because writing code doesn't feel like a very creative process, but the point is that the barriers to doing things are removed when you start programming. If you reach a limit on what you can do, you can just look at the source code and change it. That may sound easy, but it's not, and I'll come on to that. And also, finally, it's about doing practical work that's beneficial. So we want geocomputation to be socially beneficial. So there's all these ingredients in the history of the word geocomputation that we want. We want to take the good parts, and we want to remove the lack of reproducibility as a bad part, and kind of take the word geocomputation forward. So we define it as harnessing the power of modern computers to do things with geographic data, also a very broad definition. Okay, so what's actually in the book? You know a little bit about the motivations behind writing it, and you know what we mean by geocomputation. So the first chapter actually builds on this and kind of talks about some of the history of it. We've had a fantastic contribution from Roger that goes back quite a long way into the history. But then we go straight into actually doing practical examples. You learn programming by doing programming, not by reading about programming. So these are all based quite heavily on lots of code chunks, and we expect the readers to be reading it and then actually typing in and reproducing the results as we go on. So chapter 2 basically starts from nothing. this is how you install RStudio. There's a link that tells you how to install RStudio. This is how you create an SF object. So we're starting from quite basic foundations and then building up with class definitions, spatial and attribute operations, using the tidyverse. We talk about projections because projections is something that always causes pain when people are learning geocomputation. And then we move forward to talking about data reading and writing. So data I/O means input and output. So that's the first part, which is the foundations. And then we do extensions, which is basically stuff that's a little bit more advanced. So we have some more advanced methods in there, including advanced mapping. And I think visualization is actually quite a basic skill. So we also cover visualization in the foundations, and also how to build your own functions. We've got some stuff on machine learning in there, and more things I couldn't fit on this slide. So I've only got 2 of them. And then finally, we've got a section on applications. So we've got 3 chapters in there. One of them is about transport modeling, which is basically my chapter. My kind of hobby is applying these to transport applications, or my field of application. We've got one about ecological examples, and we've also got one about geomarketing. And we picked those applications specifically because in the literature, in other books, these are areas where geocomputation or geographic software in R has not been applied. There's loads of books, or there's loads of research on spatial epidemiology, but there's not a huge amount on the topics covered here. So this is just an overview of the book, and because it's all online, you can kind of select which chapters are most appropriate for you, but we definitely emphasize these foundations. We think these foundations are important for any application. And we cover raster and vector data in quite a lot of detail in roughly equal measure there. So that's what's inside the box. Okay, so one of the key definitions of geocomputation was about doing it. So our kind of attitude is a little less conversation, a little more action. So lots of our code, lots of our book contains code examples that we expect people to reproduce. And to quote Tom Hengel from this morning, the sky is the limit with R. So just take your ideas and go for it. The problem is that when you try and just go for it, sometimes this happens. You have this really beautiful idea of a geographic problem that you're going to solve, and then you start to put together the ingredients, and that happens. So how do you deal with that? And I think that's a problem with teaching. We've all been using R for many years, so we're presenting the finished product. But actually, there's been a lot of pain and a lot of broken stuff as we've been building. So that's something that we want to kind of encourage people to do and play with. So on that note, if anyone has got an R session running, I'm going to do a very minimal, hopefully reproducible live demo that people can try and copy. And unusually for me, I'm going to try and use the terminal rather than RStudio because it kind of shows how far things have come. So the first stage, if anyone's starting, just a hands up, who's up for trying a very quick, minimal, reproducible example? Okay, so you've got a handful of people. That's good. I'm going to try and make this bigger. Can everyone see that? Give me a nod if you can see that. Make it one more. And we can go into the R, which is a command line language, which runs in the terminal. And when we started using R, or for many people, that's just what you got. You had your command line, and you had to figure out things from there. But the first thing to do is install packages. Auto-completion is an amazing thing. So put your hands up if you use tab auto-completion. Put your hands up if you don't know what tab auto-completion is. Anyone? Okay, so a few people don't know, and that's fine. So tab auto-completion is when you type the beginning of a function and you can't remember what the last part of it is. You just need to press tab and it will autocomplete. And it will complete up to the last available kind of unique string that matches it. So I just pressed tab once and it went from install to install. And then it doesn't know what to do next because there's two options. If you press tab again, it shows you what the options are. You've got installed packages or install packages. They're two very different functions. One of them tells you which packages you've got installed on your computer, and another one instructs R to install a new package. So I can say install.p, and because I'm a lazy typer, I don't want to type out the rest of that function name. I'm just going to press tab. And R very kindly completes that for me. Then I'm going to open a parentheses and type in the S blanks, the name of the S blanks, the name of the S-Planks package, and if I run that, it will go away and install that. I'm not going to run it because I've already got it installed on my computer, so I'm just going to load it. So this is called loading a package, is what most people call it, but I've been told by our developers that the correct term is attaching the package. So you can type in sp-lanks, and something's happened. Some packages load silently, but other packages give you a message. sp-lanks is one of these packages that tells you something. And this is going back in time. This is loading a package that was written, I think, over 20 years ago. So it's fantastic that it's still working, and we can start to do stuff. So can I just get a show of hands who's got to this stage? Who's doing the live example? That's fantastic. We've obviously got a skilled audience, and we can load some data. So in the sp-lanks package, there's a data set called bodmin, and we can load that data set. And we can do some geographic visualization, not with map poly, I think it's called polymap. So again, I've forgotten what the function's called. I just typed in the beginning of it and pressed tab, and I can see there's two functions. One's called polym, I don't know what that does, and one of them is called polymap. So I guess that that's going to give me a map of a polygon, and because I've read the documentation, I know that bodmin has got something called polygons. So I can execute that, and I get a map of this bodmin area, which is pretty handy. So this is what spatial data visualization looks like. The fundamentals of it haven't really changed much in 20 years. You still enter commands, and you execute them, and you get a result. The next thing to do is add another layer. So usually, geographic data, you have multiple layers. Each data set is represented in a new layer. So I'm just going to add another layer to that by saying point map. There's various ways of doing this, by the way. So you can say point map as dot points and then bodmin. So I think as dot points bodmin is going to return a matrix of numbers, which is basically like a data frame, but every row and every column must be the same type. And in this case, we've got numeric data. And there's one more thing that we need to do, which is say add equals true. And I execute that, and you can see that I've added my points. That's really useful. You can add things on top of each other. And you could imagine that from these quite simple foundations, we could build up quite a complex map with multiple layers. The final thing that I'm going to show that I think is really cool, that I imagine Barry Rowlingson, who's already been mentioned, helped to create this functionality that I did not know existed, is there's a function called zoom. And again, I can use tab auto-completion. And then it says enter 2 points on the zoom area. And I can do that. So imagine that you're interested in the north of your map. Oh no, the data's disappeared, so you have to replot the data again. So I'm just pressing up to get back to my original thing, and then I can say add equals true, so it adds to the initial canvas. So this is what interactive spatial data visualization looked like 20 odd years ago. And we can, again, plot the points there as well, so I just press up and add them. So that's really cool. But there's big problems with this approach. Number one is I was hoping to show how far we'd come by putting this on Tim's map view package, but I discovered that this wasn't actually going to work because there's no spatial reference. So what I mean by that is, I'll show you now. So as.points bodmin. Okay, you can see that I've just got a matrix here of points. What happens if I convert that into an SF object called P? This means from the SF package, as SF, and I'm not actually sure if this has dot points. Will it create that? No, because I need to create some point data. Okay, so to build up, this is, we need to create a data frame first because it's a data frame thing. So we could say df equals as.dataframe. And this, I think, illustrates the point that it's easy to think what you want to do. I want to put this on a map, but when you actually come to think about how do I do that, you have to stop and think quite often. So hopefully this will work. So I've got a data frame called df, and I can ask what the names are of the data frame. And I've got something called arx and ary. So hopefully I'll be able to use this to create an SF object called P. I'm going to give it a go. Edza can probably tell me if I make some mistakes in my code, but it's good to try it. Trial and error is a very common way of learning it's a very common way of learning to program stuff. So st as SF, and I can auto-complete that. And I can give it the df object, and I can give it this coords. I think coords is up, and then you have arx and comma ary. Okay, so I've created a new object called P, and as Edza mentioned, this object has a duality. It's simultaneously a data frame, which is a very old R class definition, and an SF object, which is a relatively new. So we've taken a very, very old class, which was the bodmin dataset, and we can look at what class this is with class bodmin. And it's just a list, okay? So it's not even an S3 class at all. It's just a list of objects, whereas SF has taken this forward, and we have a bit more structure in here, and it's something called SF. And we can use the map view package to map it. And I've tried this already, so there you go. I get my auto-completion on map view, and there we go. I've got my demonstration of what happens. For some reason, I'm not getting a backdrop in here. I'm not quite sure why that is. Probably because it doesn't know where it is, what the spatial location of it is. Yeah, exactly. So when I tried it before, I got a load of points scattered around the equator, and at least I had a base map here. So the point of this exercise is to show that actually spatial data is not easy. It's hard. Things are going to go wrong. And even if I had a map, those points would not be where they're supposed to be in the north of England. That's because we don't have a spatial coordinate system. Does anyone know when the Proj4 library was released? Does anyone use the Proj4 library? It's probably after this package was released. But in any case, the SP-LANX package doesn't use Proj4 coordinate reference system. So that means, going back to Tim's talk, that there's no reference point for these points. They don't have a coordinate reference system to be based on. And going back to my slides, I've just demonstrated that, basically. So you need to understand the reason why things break. Things are definitely going to break when you're writing code, and understanding why that happens and being able to debug it and understand it is a really good point. It's a really powerful skill. So moving rapidly on, I hope, I'm going to talk a little bit about, after some observations, I'm going to talk about geographic visualization. I personally think geographic data visualization is a vital component of geocomputation, and the reason that I encourage people to do that live demo is not because I think you should use SP-LANX. I don't think you should, but I think you should be aware how lucky you are that interactive data visualization has moved forward so long. So the observation, the take-home message from that is not SP-LANX, don't use it. It's saying R is robust and future-proof. It's amazing that that code that ran in 1993 still runs today. And you can see a video of Roger demonstrating how R worked in a version of R from 1997 still runs today. So this means that R is a very robust system and it's future-proof. And I think a lot of proprietary GIS products, you couldn't say the same thing. If I tried to run a version of ArcInfo from 20 years ago, I think I'd find it much harder. So that robustness is a very important point. R's and the second one, or the third one, is that R's capabilities have evolved very much since then. This isn't really going to be a case study. I'm going to skip through these next slides, but I'm going to talk about a few examples of geographic data visualization and show some images of how visualization as a subfield of geocomputation in R has evolved rapidly. There's been a huge growth in the number of packages and the diversity, which is great, but in some ways it makes it difficult because you have to choose between maybe 5 packages, which takes energy. So we've got some consolidation, but there's still many packages, and plot is still best for many tasks, which is quite a mature function that works in base R. So maps are very important. That's the point of this this next set of slides. And maps go back a huge amount of time. In a way, you can trace the evolution of civilization through maps. So some of the earliest kind of depictions that you find are maps of areas. So they've been vitally important to humans for a long time. And I think it's worth placing your own maps in the context of what's gone before. So this is just an example of a map that was created a huge amount of time and drawn in stone that we still have. People also use maps to understand the world. So there was a more kind of philosophical purpose for the map to say, well, this is my place in the world. So this one, it's not even trying to be an accurate portrayal. It's just saying, this is our understanding of the world. So it can transmit a much more powerful or deep message than just scientific information. And I think that's worth taking into account. And moving rapidly forward in time to the 1800s, we've got a beautiful, this isn't even a map, but it is a geographic data visualization, because you've got, across the x-axis, you've got geographic space, and instead of having another geographic coordinate on the y-axis, you've actually got height. And this was a geodata info visualization from the early 1800s by Alexander von Humboldt. And this represents his worldview of how ecosystems change in kind of systematic ways over time. So the point here is that geographic data visualizations can be creative than just a simple map on a page. So that's another example of a very powerful visualization that's actually had a huge impact on the sciences from when it was created. So moving forward much more quickly now, in the ASDAR book, Applied Spatial Data Analysis with R, it was stated that R was not designed for the display of interactive facilities, and it has drawbacks in this area. 5 years later, we've got Leaflet, and we've got map view. So this is one of the core limitations of R that we all used to experience that has been overcome. So that's a huge amount of progress that has been made. And very quickly, we've got how base graphics work. So you load your SP library, which was the predecessor to SF, and you plot a map like that. I'm not going to show the result of that. Now with SF, you have color schemes by default, and you can create facets very easily. But in geocomputation with R, our emphasis is on the TMAP package, because we think it's a very powerful package for visualizing spatial data, and we want to teach people the stuff that's most likely to be useful to them. So it's concise, and creates attractive maps with minimal code, a little bit like ggplot2, but it's more specific to making geographic data. One of the amazing things about TMAP is that you use the same code that creates static maps can also create interactive maps. So that's a really powerful feature of the TMAP package, and it's well documented. Again, I'm not going to go into this, and I'll be covering spatial data visualization in the workshop on integrating spatial data into tidyverse dplyr pipelines on Wednesday. Another thing to mention is that there's also been progress in more kind of innovative ways. So it's now easy to create animated maps, which is really useful. And as we'll find out tomorrow in Tim's talk, it's become super easy to create interactive maps with MapView. Okay, so I've made the point that interactive data visualization is a very important part of spatial data with R. So the second point of just doing it is, what are you going to do? We've now got so much data and so much software that we can do things that would have been impossible 20 years ago. So something that I've said before is that geographic data can save the world. That may be a bit of an overstatement, but the point is that you can use these techniques to tackle real-world problems. But again, one of the most intriguing things about spatial data is that you can think of what you want to do easily and say, okay, I want this data to be visualized on that map, but then when you try and do it on a computer, it can be surprisingly difficult. So again, don't feel like things are going wrong if you get error messages, basically. That's the point here. So again, I've got this message of, yeah, we're going to save the world, and again, things go wrong. Don't give up. And the message that I wanted to convey here is that I think it's really important that we identify problems that are actually beneficial or useful. There are almost infinite directions that we can go in our spatial data analyses, and it's really important that we think about this. So this goes back to a definition of geocomputation by Stan Openshaw in 2000, and I think this is something to think about, is our research actually beneficial? It may be beautiful, it may be fun, and it may get a lot of likes on social media, but is it actually useful? So a few ideas about things that are useful, and I think everyone in this room is probably tackling one of these issues. In terms of Earth, how to replenish topsoil, that's a big issue, is topsoil degradation. Obviously, these skills can be useful for understanding topsoil degradation, general biodiversity, and also some of the underlying geology. And I know there's a huge amount of application in this area. Water, how to deal with aquifer depletion. I haven't seen hardly any geographic data on aquifers, but I'm sure this is an area that is hugely important for the future. And the skills that you will learn during this summer school, or that you already know, could be really useful for understanding this water problem. And something that's very relevant today, having had a summer with huge numbers of wildfires across Europe and other continents, is how to encourage fire-resistant ecosystems. So in a time of climate change, this is a real priority, I think, this research area. So how can we use geocomputational methods to solve different problems? And this is something that got me thinking, because I have my area of application, which is transport, but I said to myself, if I were to go back 5 years, would I have done something different? And I think it's never too late to kind of experiment, and it's always good to try out new applications. So I'm very interested in learning how my skills could be useful to tackle some of these big societal issues. And that brings us on to the topic of justification. Everyone justifies their research areas, and I think subconsciously many of us justify them retrospectively. So in terms of the previous examples, it's clearly justified by evidence. Why study it? So are there more important issues out there? That's something to think about, I think, which is a bigger question. And I'm just going to provide an example of something that I think is really important that fits into the water category here. So I've been reading up on climate change and the impacts of climate change. Everyone knows that climate change is a huge issue, but often people just leave it at that. It's a big issue. Why is it a big issue? From what I've read, sea level rise is the one impact of climate change that's going to have the biggest societal impact. And I think it's also the aspect of climate change that is possibly most conducive to geographical research, because elevation across the world is so unevenly distributed. So here's some evidence. I said we should base our justification on evidence. There's a huge amount of evidence that sea level rise is a big issue, and kind of cutting edge science supports this. So I guess what I'm trying to say is that justifications like I like bikes, which is the justification that I use for my research, may not be the most appropriate. Preemptive justifications, such as this is the #1 area I can make a difference, is a really good justification. So I'm just getting people at the beginning of this summer school to think about what are the domains that I want to study. And especially if you're at the beginning of your career, it's really important to think about why am I developing all these skills? So this is just something that I want to think about, and the point that I want to make is don't be like me and be retrospective in your justification, be preemptive and look at the scientific literature and base your research on that. And the great thing about a summer school is that you can try a different area, be creative, don't just continue to do the same thing that you've been doing for the last year or so. This is an opportunity to be creative. So just an example, a case study of doing something useful that links to my own research. I'm not going to do a live demo of this, but we created an interactive web mapping application that is being used by local government, and it's called the Propensity to Cycle tool. There's an open access website that anyone can go on called pct.bike, and planners are using this to build an evidence base to help plan for sustainable transport systems. So hopefully it is doing something useful, and just trying to imagine what the end product of the research could be is really great. And this links back to my slides on visualization, because it was the visualization side of this that made this important. If we'd done the same analysis and just saved all of the results as a .rds file and then gave it to local practitioners, nothing would have happened. The reason that this has made an impact is because of the visualization. So that just reinforces my point that visualization is vital. So going back to my sea level rise example, I think I'm almost over, so I'm not going to be able to do the full reproducible example, but how can we prepare for future sea level rise? I think that's a really interesting question. I want to investigate that more, and I've created quite a simple starting point for understanding this. This image I find quite shocking. I read it in a scientific journal, and this is 0. This shows where sea level rise is currently. And these guys, unlike most climate researchers that go up to the year 2100, they decided to go 10,000 years into the future and say, okay, what's likely to happen in 10,000 years? And you can see that their models suggest that you're going to have not just a little bit of sea level rise and then it stops. It starts going, and then you get positive feedback, and it just keeps increasing. And it could go to up to 50 meters higher than what it currently is. What's the impact of that on civilization at the moment? I don't know, but I can bet you that geocomputational or geographical analyses can help understand that. What are the implications for the locations of ports? You could have a research program just looking at how maritime ports need to move based on this information. So I think we should try and think big, and we should tackle really big long-term issues like this. And something that I've found useful in my research that links back to the image of von Humboldt's kind of nature, his visualization, is that sometimes it's better to be broad and big than just focus down on very specific details. So if you take a global analysis over 10,000 years, you're not going to get a very high level of spatial and temporal accuracy, but in terms of the results, you might have something that's really useful for the world. So I've got a reproducible example. I'm not actually going to run through this because it will take quite a long time, but what I can show you is, if I open this in a new tab, this is just the GitHub repo that hosts the slides that I'm using, and I created an issue in here. So this is GitHub, and I just created an issue that says how to reproduce the code, and it also gives me an opportunity to illustrate a really fantastic thing that enforces reproducibility. So could people put their hands up if they've heard of this function, reprex? Has anyone heard of that? And keep your hands up if you actually use it. Okay, no? So what reprex does is you give it some R code, and it tries to reproduce it. And you have to have absolutely everything in there. And you can include quite a lot of data. So here, I've even got the data download in here. So I commented it out, so it didn't take 5 minutes to download, but you download the data, you unzip it, and then this just shows that every single line of code here is being run in a separate environment that demonstrates it. So I'm starting off with a very low resolution map of the world. This is Poland, believe it or not, in the shape of Casper the Ghost. And I've used a function here from the elevator package to get some elevation data. So you can uncomment that code and it would work, but I've saved it already. And I'm imagining a 10 meters of sea level rise, which is roughly 1/5 of the sea level rise that was expected from that previous research. And you can see that sea level rise is going to affect the north coast of Poland. I was going to use the Czech Republic, but it's too far away from the sea, so I decided to just go north and look at the coast there. And you can see, though, that it does actually have some inland impacts. So this is just an example of how geocomputation can be really useful to look at issues like this. I also got a separate data set from NASA, which is much higher spatial resolution, so you can start to zoom in there. And then and then I did some validation. So this looks, after you aggregate the high-resolution data set to the same spatial resolution of the low-resolution data set, do you get the same results, which is an important part of any scientific research? And yes, you do. And the final question that I was asking is what percentage of a city called Szczecin or at the regional district might get flooded under a scenario of 10 meters. And we can end up with a final representation of that map. And in a way, it's not the color scheme, it's not anything about that map that's important, it's just the concept of showing this is the area within a city that could get flooded. If you want to have impact, it would probably help to publish this on an online interactive map. But I think the main point is choose your topics well. So that's a reproducible example that I was going to go through in my RStudio session, but I'm not going to do that. You have to trust me that that works, and you can try it on your own computers. So just to finish off, what's next for geocomputation with R? I think this is a good question. We've written a book, but in a way it's just quite an introductory book that talks about here's what you can do, here are some packages. I think in general we need to do some consolidation of what already exists. So we'll be talking about that on Wednesday in the workshops. There's a lot of areas of growth that are not covered in the book. So there's growth of cloud services and containerization of geographic software. So there's something called Docker, which allows you to spin up any kind of geographic software, and you can use that that really helps with reproducibility. And then there's this question about what's the future of raster and how do we deal with large raster data sets? Because when I tried to load a elevation model for all of the world, it just crashed my laptop. So I really need the big data, the big raster software that Eds is going to be talking about to solve some of these big problems like sea level rise. And there's also integration with other languages like Python, and I think there's a lot of potential for more bridges. So geocomputation with R is not finished. We've almost finished the book, but in a way, I think we're just at the beginning of kind of a huge amount of innovation in this area. So thank you very much for listening. Sorry I've gone slightly over for coffee, but if you're interested in the references or have any questions, I'll be happy to take any now or after during the coffee break. So thank you.
Okay, well, thank you, Robin. If I can summarize the two things I heard that you said important for this class. One is use this time of the school to also to try new things. And so I think you all already are users and you're doing analysis, but use this opportunity to experiment a bit. So be ambitious. And if things don't work, don't lose hope. We also crash computers, as you see, and we crash our sessions, and we also produce something which is actually scientifically not supported, and so it happens to us too. So two messages, if I heard from you, if I'm right. I don't know if you want to add to that.
Yeah, just go for it. And I think, yeah, trying new stuff and discovering new data sets, this is the opportunity to do that. So I'm interested in sea level rise, and if anyone has some information or some ideas about this, then we can look at that as like a new mini project, and don't just use the data sets that the workshop instructors give you. Try and find your own data sets and apply it to problems that you're interested in, I think.